Oh, hello, class. What's going on? Just getting some light in here for once. Here we go. Back in the old room. Where should this go? Let's go over here. Getting the webcam set up. How was everyone's Wednesday?
It's chill. How's yours?
My Wednesday was amazing, man. Thank you so much. I took my first nap, I think, in years.
That sounds great.
It was pretty nice. It's pretty nice. I haven't slept in years. No. Okay. Isn't that kind of awesome? Thank you very much. I love it too. There's also a beard below it. I thought that looked fun. But and by the way, that's not even the side of the room that's meant to be visible on Zoom. Let's just be facing the other way. It's my desk facing the wrong way. So this is the bad side. Just wait till you guys can see what's on the other side of this wall. And you'll get a vlog-worthy treat over here. I don't vlog, but I always want the option to. God, that was the webcam. Whoops. All right, so let's plug this baby. Online classes? Good? Bad? What are you guys thinking? The way JMU went, it's looking like we might be going there soon. You guys hear that news?
Yeah.
It's a talk show. Did you hear about JMU? For a plug. Aha. I do this, and then I do this, and then we click this button to get this extra screen going. Nice. We are in for the day. Cool, cool. Well, welcome back, everybody, to Discrete Math Lecture 6. Yeah, Lecture 6. What's going on? We are now past a handful of lectures. So welcome. Welcome to the interior of the class. How's it going for people? Anyone have any questions, comments, concerns about the class? I should give out, you know what I'm gonna do? I should give out like they always do at like Walmarts and stuff like that, where it's like, hey, if you fill out this survey on the receipt, you get 20% off your next thing. What if I make you guys fill out a survey and you get like 1 extra credit point? Ooh, that's better than 20% Walmart.
I'm down.
So the survey for if we should take a survey is looking good. It's just like those pre-trial trials. Just a bunch of things going in circles. Okay, so anyway, if no one has any questions, let's just get back to what we were talking about. We're gonna finish 2.2 today and then move on to 2.3. So let's get going with 2.2, the end. I think I've been saying the pages that this is like Karate Kid, the wax on, wax off, all that. If you haven't seen Karate Kid, I recommend watching it. Don't watch the Jackie Chan version. Watch the Ralph Macchio version. All right, but anyway. So to finish up section 2.2, remember this is about conditional statements. Which are the statements that have the structure if P, then Q, or another way to write that, because we can say P implies Q. That's a lot of times we write that. Or you can say, you can write it like that in the more mathematical notation. Or you could say, in my notation, if then PQ. I should tell you guys that like writing if then or like and then putting the P and Q there, or writing like the and or the or, PQ, all that kind of stuff, that is just for this class. That's just what I use to help you guys think. This is not necessarily standard mathematical notation. If you, oh wait, can you guys see that? If you wrote that, people might not know what you're talking about, but I think this is a good way to think about it, and that's why I do it. The point is, I'm recording this, so in the future, if this ever comes up and you guys are like working at Google or something like that, and this comes up, you cannot blame me. I will have this locked and loaded, this recording. Anyway, yeah, that's what conditional statements are. Now we're going to talk about a few statements. We're going to talk about today. What's a good color for today? Someone pick a color.
Purple.
I like it. That's the right answer. Then we're talking about inverse converse, and contrapositive. And this is just kind of like inverse, converse, contrapositive. Remember, this if then P, this P implies Q, this is a statement. So this arrow, and we got the focus thing again. But this arrow right here, this is an operation. And so inverse, converse, contrapositive, you can think of them as all different but related operations. You can think about them that way. But none of them are the negation. We talked about this last time. None of the negation. Wow, that purple looks blue, doesn't it? I swear this is purple. Wait, look at blue next to it. Oh, they look the same. Interesting. Anyway, sorry. The point is that none of these are the negation. We were on the negation last time. Recall. Put this in the corner. Negation of P implies Q is, we can write it like this, and it equals P and Q or not P. If not P, you're vacuously true, but if P is true, then Q must also be true. That was the reasoning for this. Anyway, though, none of these are that. Inverse, converse, contrapositive is not the same thing as the negation. They are very different. So let's just go through it. The inverse of a conditional statement, P implies Q, I'm going to write it like that. It's just like what you'd say. What that is literally defined to be, I'll do like a little semicolon to let you know what's defined. Actually, I guess I have a triple colon because there's 3 equal signs. I don't know. It's literally defined to mean not P implies not Q. And then the converse of P implies Q, that's defined to be the statement Q implies P. And then the contrapositive of P implies Q, that's a weird one. Inverse and converse kind of makes sense. Like, oh, you can't see that. I'm sorry. Someone speak up next time. Inverse and converse, they're both in with verse. How'd you guys know what I was talking about? Verse, in fact. So, oh my God, they have an inverse, but not the I. Anyways, the point is, yeah. So inverse kind of makes sense. Like you're inverting both P and Q. Converse, I don't know, it kind of sounds right? Like converse it kind of sounds like you're flipping things around. Contrapositive is the one that comes out of nowhere. Contrapositive sounds like it sounds like some kind of a snake from South Africa or something like that. I have no idea. It sounds like if you test positive for some sort of disease you get from a snake. That's what I think it is. Anyway, the point is, what this is going to be not Q implies not P. So the inverse, the converse, and the contrapositive of a conditional is itself another statement, but it's different. Or it looks different at least. I will tell you. Or let's just go through it. So they look different. Do you think any of these is actually equivalent to our original statement? What do you guys think?
No.
Toru says no. Possibly. That's a much more measured answer. Right, that's good. See, I feel like, Toru, if you're going off of the tone I use to speak, because usually if someone says, do you think any of these are the same? The tone means no, but I'm terrible at acting. So the point is you cannot trust my intonation in the slightest. Sid is right, but in the worst way possible. Sid's vacuously right in a sense, because like he can never be wrong. Possibly, everything's possibly true. You know what I mean? Am I the sexiest man alive? Possibly. So Sid, are you want to take a better stand? Oh, sorry, that was you said. I'm sorry. Who said possibly? I thought it was Sid. I saw his thing pop up.
Oh, that was me, Safa.
Safa. Okay, you got a better answer than possibly? Come on, take a stand with pride, Safa. You're like Aaron Burr here.
I mean, I say possibly because the only way to find out is, I guess, to do some truth tables, and I can't do all those in my head.
Exactly. That's a perfect way to think about it. The way to find out is doing some truth tables. But I will tell you right off the bat that Toru, you are 60% right, which in a certain sense is better than not answering. You know what I mean? And that is that the inverse and the converse are not the same. This is, and we're going to show why. This is not equivalent to P implies Q. This is not equivalent to P implies Q. These are very different statements. However, the converse, interestingly enough, if you both switch the order and flip and negate both sides, this is the same thing as P implies Q. But anyway, interestingly enough, this is a lot easier than this. Most people they come around to the fact that the contrapositive is equivalent to the original, but a lot of times people make this mistake and they say, oh, this means this or this means this. Do not make that mistake. Everyone here is better than that. And I dropped the one piece of paper I needed. Is my face really close to the camera? There we go. All right. So, what are we doing next? Oh, yay, examples. So, let's do some examples of this to kind of show what I'm talking about here. So, for example, let's say that P is the statement I went surfing, or I'll say I must have gone surfing. And then Q is the statement I must have gotten wet. Actually, I simply made P red and make Q blue. Here we go. So Q is now I must have gotten wet. So here's the question. Does P imply Q, first of all? If I go surfing, must I get wet?
Depends on how good you are.
That's actually a very, very good question. But must I get a little wet? In the face, maybe a little bit?
Probably.
From the ocean spray? Yeah. You know, the actual truth of this doesn't really matter. We're going to say it's true. You see what I'm saying is the point. And actually, since I said I here, right, you said depends how good I am not that great. So I will get wet. So yeah, if I go surfing, I will get wet. That is true. Can I? Yeah, cool. So now let's look at not P implies not Q, which is the inverse. So this is the inverse. I wrote inverse there. There we go. So is the inverse true? If not P is true, meaning if I did not go surfing, is it true that I did not get wet?
I'd say false.
False. Right? I cannot go surfing and still get wet. And still get wet. For example, if I take a shower, or for example, if I spill an entire glass of water on myself. Like, there's plenty of options on ways to get wet. That sounds weird. But anyway, the point is, yes, this is the inverse. If not P implies not Q, or not P does not necessarily imply not Q. So that's why I say it's false here. So even though P implies Q, not P does not imply not Q. That is false. And this is exactly why the inverse is different from the converse. This is the squares and the rectangles thing, right? Like any square is a rectangle, right? So if something's a square, you know it's a rectangle. But that doesn't mean if it's a rectangle, you know it's a square. That's exactly what this is. Now let's look at the converse. Actually, I'm sorry. That's the converse. This is saying if something's a square, you know it's a rectangle. If it's not a square, you don't know it's not a rectangle. That's it. It could just be a non-square rectangle. That might be more confusing than it's helpful. But anyway, I hope this example likes it. The point is you can't necessarily go in both directions, or you can't just necessarily negate both sides. It doesn't work like that. Those are the converse. Is it true that Q implies P? So is it true that if I must have gotten wet, then I must have gone surfing?
It's false.
Why is that false?
Cause like you said, yeah, you can get wet from other things.
Exactly. There's plenty of things. I could go running in a sprinkler and enjoy life. I could go running in the rain because life is so awesome. I could fall in a puddle. That's happened before. All these things are possibilities. You could be having a bad day and the car goes by and splashes a puddle of water on you having a worse day. Right? That could totally happen. So the point is, yeah. So the inverse and the converse are both not equivalent to the original. They mean different things because just because P implies Q, it doesn't mean you can go the other way. Just because P implies Q doesn't mean not P implies not Q. And notice we use the same exact logic here. Like, these things are actually saying the same thing in a weird way to look at it. And we're actually going to show later that the inverse and the converse are themselves equivalent, but they're both not equivalent to the conditional, the original statement, or the contrapositive. So, this is an example of, where's my wash button go? Paper towel. So this is an example of how the original statement is not equal the conditional. Any questions? All right. Let's look at another example real quick. Let's look at an example. Let's say P is pigs fly, and then Q is, what, does anyone know what a quail is? Do quails fly? Is there a bird such as the Q? Oh well. We're gonna lose the alliteration.
Quails do in fact fly.
Quails do fly? All right. Quails fly. Look at that alliteration. Isn't that nice? This is the above and beyond that I put in this class for you guys. It's the alliteration. Yeah, so pigs fly. So pigs fly, quails fly. So here's a question. Does P imply Q? Right now it's a question mark, but hopefully not for long.
Probably false.
So I totally get what you're coming at. And you could definitely make that up.
Just kidding. Is it vacuously true? Yep.
Yeah. We're saying if pigs fly, then quails fly. Well, I mean, remember, that's a conditional statement. That is just telling you if P happens, it's telling you something about Q. But P doesn't happen, so it's not really saying anything, and so we say it's vacuously true. So this is true vacuously. This is just, remember, this is just because the truth table looks like this. True, false, true. Oh, no. True, 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 false, false, true, false, false, true, false, true, true. We're in this condition here, right? But like whenever the hypothesis P is false, oh, you guys can see that. Whenever the hypothesis is false, we consider it true vacuously. We talked about that last time. Okay, P implies Q is vacuously true. So in our sense of the word, in our sense of if then, if pigs fly, then quails fly. That's a true statement because pigs don't fly. Now, how about this? How about does not P imply not Q? So what's that saying? That's saying if pigs don't fly, then quails don't fly. Is that true?
No,
False. Exactly.
because it's the inverse.
Because it's the inverse. And the inverse is not necessarily the same. We'll do an example. What is the same? Is that, well, I'll show you. We'll get to that in a second. So the inverse is not necessarily the same. So I've done an example where, yeah. So we get false there, and then we get P implies Q. I'm sorry. We get Q implies P. Q implies P. That's saying.
Can't quite see that.
Oh, thank you very much. I'm glad that you trust me enough to know that I'm not just losing my mind and scribbling on the ground. There we go. Good. You know I'm actually right. Good. So Q implies P. Is that true or false? So if
Also false.
then do pigs fly? Oh, sorry, I didn't hear that. Say it again.
Also false.
Also false. Exactly right. And once again, they're false for kind of the same reason. The problem here is that, so here we're saying that if pigs don't fly, then quails don't fly. The big problem is that, well, quails do fly. You know what I mean? So that's not true. And here, quails do fly, pigs don't fly, so it's false. So anyway, it's going to turn out that the inverse and the converse are always equivalent to each other, but not necessarily to the original statement. But sometimes they are. Like, for example, if I said, let's say, okay, that's a good example of this. If I said, let's make P. P is going to be, I can juggle. And Q is going to be, I can throw things. I can throw 3 things in the air and catch them in a cycle with at least 1 ball in the air at once, which is basically the definition of juggling, right? It's very telling us where my brain went. The point is it true that P implies Q?
True.
True, right? If I can juggle, I can certainly, by definition, I can certainly throw things in the air, catch them, blah, 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 all that. Is it true that Q implies P?
True.
True, right? Because this is just the definition of juggling. And then it's also true that not P, if I can't juggle, then I can't do what basically is juggling. What is juggling? I can't throw 3 things in the air and do all that. So these are all true statements. The point being that sometimes the converse and the inverse do in fact, or are in fact equivalent to the original. Like sometimes they're not always opposite necessarily. Like the original statement and the contrapositive are always going to be the same. Sometimes the inverse and converse are the same. Sometimes they're not. Can we think about when they're going to be the same? Inverse and converse equivalent to original when what?
When one is the definition of the other.
That's kind of an interesting way to look at it. It's when I'm gonna write this way. When that happens, when you have a biconditional, basically, right? And so when you have a definition, you certainly have a biconditional. But also, and whenever you have a biconditional, you kind of have a definition. A biconditional, that means whenever P is true, Q is going to be true. Whenever Q is going to be true, P is going to be true. Whenever P is false, Q is false. Whenever Q is false, P is false. When you have a biconditional, this means P and Q will always go with each other. They'll always be the same thing, which basically means P and Q are just different ways to write the same thing, right? Does that kind of make sense? If you can go both ways, that means that there's different ways to write the same thing. Whereas, like the surfing, like if I go surfing, I'll get wet. That's a little different because there's a lot of ways to get wet other than going surfing. They're not the same thing. But here, if you go both ways, P and Q are basically just ways to rewrite each other. Does that make sense? I'm not getting that it doesn't make sense. And so by the common law definition of making sense, I'm going to say it makes sense. Good, yeah. So that's what converse and inverse and all that's all about. So now I've said that the contrapositive, in fact, is in fact equivalent to the original statement. And I got no pushback from that. Probably because you guys respect me, right? And it would probably be kind of a jerk move to immediately start to question it, right? But now it's time to question it. So let's think about why it's true. Why is contrapositive equivalent to original? That's the big question. And all of those letters are terrible, but I think the general shape of the word actually looks correct. This is like impressionist writing right here. You squint, you see it. The point is, why is contrapositive equivalent to the original? Well, think about this. Assume A equals, not equals. Assume A implies B is true. Then, if not B is true, let's think about this. So A implies B is true, meaning whenever A is true, B is going to follow. Whenever A is true, B is true. If not B is true, then firstly, B is false. Then B is false. Right? That's just simple. But now let's think about this. Consider if A were true. So let's consider for a second if A were true. If A were true, what do we know about B based on this?
B also, actually, I was gonna say, it also has to be true, but I don't know if that's true.
No, you're totally right. Because A implies B is true, because this is a true statement, then since A implies B is true, by the definition of the truth table, right? If the first thing, if A is true and the statement is true, Q must be, like the second thing must be true. I mean, what I'm saying is if A implies B is true and A is true, then B must follow. So since A by B is true and A is true, B must be true. So I'll put it this way. I'll say assume this is true and also assume not B is true, which implies B is false, which means B is false. So in this case, we're assuming A implies B is true and not B is true. If we consider A being true, that would mean that B must follow. B must also be true. But we assumed not B is true, meaning we assumed B is false. However, However, we assumed B was false. So A cannot be true. So the point is, if A were true, that would mean B is true based on this, but B is false. So we can't even have A be true. Like that just can't happen. It leads to a contradiction, right? B can't be true and false at the same time. Why can't B be true and false at the same time?
Then it wouldn't be a statement.
It wouldn't be a statement. Exactly. That's this day one coming back. Day one, we said a statement has to be true or false, or actually day two. Day two, we said a statement has to be true or false. It can't be both. We said that's the law of the excluded middle. And I kind of told you guys, like, hey, this is just what we're going to assume. Everything in this class we're dealing with statements. It doesn't necessarily mean it's true. It doesn't necessarily mean it's like true with the real world. That's just how we're going to work in math. And so this is true so this is true if you assume the law of the excluded middle. If you assume that things can't be both true and false at the same time, which isn't that bad of an assumption, then you know the contrapositive is the same thing as the original statement because of this right here. This makes sense? All I'm saying is that all I'm saying is that if A and B is true and you have not B, A can't be true because that would lead to B, which you know is false. Meaning, thus, not A must be true, because if A is not true, not A must be true. So, not B does lead to not A. It's kind of confusing, but I hope it makes sense. And think about it this way. Assume this is true and assume not B is true. You have two options for A. Either A is true or it's not true. If A were true, though, it would lead to this contradiction. If A were true, then because of this, you know B must follow, so B is true. But we specifically know that not B is true. We know that B is false. So since the only options for A are true and not true, A must be not true, and so then you have that this follows. Does that make sense? Well, anyway, let's not get too hung up on if that exact explanation makes sense, because we're not just going to leave it to that explanation. We're of course going to prove it with
Truth table.
Oh, truth table. Wow, Dutch angle for a second. Does someone type in truth table? There we go with a TT. Thank you for that. Yes, with a truth table. So real quick, let's have P. Let's have Q. Let's have not P. Let's have not Q. Let's have P implies Q. And there's a lot of space for that. And let's have not Q implies not P. All right. So you have this, and the cases you have to consider again are true, 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 false, false, true, false, false. So the first three of these are easy. So if P is true, not P is false. In the case where Q is true, not Q is false. And then P implies Q. Remember, P is true and Q does follow. So this is true. And you can look at this truth table, the definition of if and to figure it out. Or maybe I'll put here, this is like if then, if you plug in true, true, which will come to true. Not Q implies not P. So here, this is a conditional statement where you're saying not Q implies not P. So this is like taking this if-then operation and plugging in not Q and not P. And then that would be not Q we know is false. Not P we know is false. And so and you plug false, false into an if then, oh, that's true. It's vacuously true. So we get true, true here, that's good. Any questions on that? Because if not, we can blow through the rest of this because the rest of it's just the same basically. Good. So then in the case where P is true and Q is false, not P is going to be false. not Q is going to be the opposite of false, which is true. P implies Q is false. This is the one case it's false because P happened but Q didn't follow. And then here you can think about this as it's if then, not Q, not P, which is if then, not Q in this case is true, not P is false. So here we're going to get, the true false thing where you plug the T is the first one and that false the second one, and that's false. Only case where it's false. And then it keeps going like that. In the case where P is true and Q is not true, when P is false and Q is true, you get not P is true, not Q is false. Since P is false, P implies Q is vacuously true. And then here, this is like if then, not P, Q, not P is not P, not Q, not P is false, not Q is true. When you plug a false true in, you get vacuously true again. And then finally, if you plug in the case where P is false, Q is false, not P is true, not Q is true, P implies Q is vacuously considered true. We're in the false part here. And then here we have if then, not Q, not P, not Q is true, not P is true. And so if you plug in true, true, and if then, you get true. So these two columns are the same, meaning I hope the explanation of why they're the same makes sense for their intuition, but if it doesn't make sense to you, just believe it here. The truth table is the same, so they are true. Any questions on that? Perfect, cool. Any comments? I mean, this is kind of interesting. Like, I feel like when we do the truth tables, it just kind of feels like we're doing a bunch of computation. But really remember what this means. This means that P implies Q is the same thing as saying not P, or not Q implies not P. This is incredibly powerful because this is the first one we've really done that's not entirely obvious. Like, it's not entirely obvious that not P implies not Q is the same thing as P implies Q. And so here's where we can really, I told you before, like the reason you want to rewrite a statement, like using the equivalences, like we had our laws, you can rewrite them. The reason you can rewrite a statement, or like one reason you do it is because sometimes it's easier to prove the truth of one than the other. This is one where that can really be true. Sometimes it's a lot easier to prove this than it is to prove this. Even though they're equivalent, it might be a lot easier to see this solution, which is interesting. Yeah, and you guys will see all that later. But we're going to call this the contrapositive law, by the way. This right here, the fact that the contrapositive is equivalent to the original, we're going to call this contrapositive law. So if you ever use this in like an argument, like one of those statement things, one of those statement proofs we went over, we had to do like by this and the equivalent by this and equivalent by this. You can say by contrapositive or by contrapositive law. Sound like this. That's fine. Yeah. So I'll say, is there a chat message? Yeah, look at that. Marcus has an excellent chat comment. I'm not going to say it out loud. You can read it. Actually, I'll say it out loud. I'll say it out loud for the people at home. Can we prove that inverse and converse are equivalent by just saying that the inverse is the contrapositive of the converse? I think that's a good idea. However, I'm not gonna tell you because it's gonna be one of your homework 2 questions. I'm gonna tell you the fact that not P implies not Q is equivalent to Q implies P. And we'll call this inverse converse law, but proof for homework. But it's not hard. All right. Anything else? And remember, none of these are the negation. So let's talk about some different ways that we hide if-then statements in English, and what they actually mean. We're still on 2.2, and I'll call this. If this could just not be it. Hello. Focus. You got this, camera. Okay, I'm gonna start writing and then hopefully work itself out. So I'm gonna call this interpreting hidden if-thens. They're hiding out there among us. So, can you just focus, camera, just a little bit? A little bit? I will eventually get the actual focus on. The problem is I think the way I have this set up, the distance changes every class. Hello? Hello? Is there something in the way of it? Is that the problem? What is? Aren't you glad you came to the in-person lecture to get this kind of exciting content? Yes. Keep focusing. No. Focus on this. Yes. Aha. Nice. Good. So, derby hidden if-thens. So the first one is only ifs. And these are kind of interesting. So let's say if someone says along the lines of, where'd my notes go? There we go. If someone just says something along the lines of, R only if S. So R and F are statements that say R only if S. Let's think about what this actually means. What they're really saying is that R only possible when S is true. So R is true is only possible when S is true. And R is only possible when S is true. That's really saying something about the negation. It's saying R is only possible when S is true, meaning when S isn't true, R can't happen, right? So this is saying if you don't have, if not S, then not R.
Does that make it vacuously true?
This statement?
Yeah, if S is false.
Oh yeah, so if S is false, so R is true only possible when S is true. Ah, no, not quite. So what this is saying is R is true is only possible when S is true. And so, well, we're kind of getting ahead of, so this is a little confusing. So this statement right here, well, we'll get to it. We'll get to it. Because right now we're, yeah. So like right now when I say R is true and S is true, I'm talking about the actual truth value of R and S, not the truth value of the statement. Like right now, we're talking about what it takes to make this statement true. So what it takes to make this statement true, if this statement is true, what that means is R is true only possible when S is true. And that means if not S, then not R, which is the same thing as saying not S implies not R, which by the contrapositive law is what?
R implies S.
So weirdly, R only if S, it kind of looks like it's saying if S, then R, but it's really saying if R, then S. Let me give you an example of that. Let's say, R is equivalent to, Dave Dave eats it, and then S is equivalent to it's hot. I'm gonna say Dave eats food, and then I'll say it's hot. The food is hot. So imagine if I said this statement, Dave eats food only if it's hot, right? So this is the original statement. Dave eats food only if it's hot. So this is R, by the way, and this is S. So this is R only if S. So is this saying R implies S or S implies R? So R implies S, S implies R. R implies S is if Dave eats it, then it must be hot. And this is if it is hot, then Dave eats it. Which one of these is equivalent to the original?
S implies R.
S implies R. So this is where it gets a little bit confusing. And it kind of depends how you interpret English. But here's how we interpret this in this class. And it makes more sense in math, maybe. But Dave eats food only if it's hot. That means Dave just eats hot food, right? He doesn't eat cold food, is what that's saying, right? But that doesn't necessarily mean Dave eats all hot food, right? Like what if he's allergic? Like, what if he just really doesn't like mushrooms? Or he's got a problem with kale, right? Or he doesn't want to eat like hot potato salad or something. You know what I mean? Like the point is, Dave eats food only if it's hot. That's not saying that Dave eats all hot food. That's just saying the food Dave eats is hot. Does that make sense?
Yeah.
Yeah. So this is saying that the only food Dave eats is food that's hot, which is saying if Dave eats it, then it must be hot, right? Because if Dave eats it, well, then you know it must have been hot. So if Dave eats it, then it's hot. If it's hot, we're not necessarily knowing if Dave eats it or not. We just know it's a potential thing for Dave to eat, but maybe it's something he doesn't like. You see what I'm saying? So R implies S, equivalent to original. This is not equivalent. The point is, R only if S is equivalent to R implies S. Not S implies R. That doesn't necessarily mean that S implies R will be false. It just means it's not equivalent. And so that means like R only if S, if you know that's true, you know this is true. That's what it means to be equivalent. You don't necessarily know that S doesn't imply R. It's kind of like the biconditional thing where we said the inverse and the converse. Sometimes though, sometimes the original statement will be true and the inverse will be true. It just means the fact that the original statement and the inverse are not equivalent. That just means knowing one, you don't automatically know the other. You have to know something about the particular situation you're in. Cool? Okay, so let's talk. Let's talk the ones that'll come up more. Only if it's come up that much, specifically because it's kind of confusing. But the ones that come up more are necessary and sufficient. We're sounding professional today. So let's see here. So another thing you might see is R is necessary for S. And what's that? Come on, there we go. And what's that really saying? If we say R is necessary for S, what that means is if you don't have R, you don't have S, right? Does that make sense? Like if I said Wi-Fi is necessary for this class, what that really means if you don't have Wi-Fi, you can't do this class, right? So not R, this means not R is equivalent to not S, which is the same thing as saying S implies R. That make sense? And so the way you think about this is since R is necessary for S, if you have S, if S is true, R must have been true because R is necessary for S. That's why if you have S, you know you have R. That's why it goes this direction. Anyway, another thing we have is R is sufficient for S. And what that means, R is sufficient for S. That means if you know R, that's enough to say S. So that just goes like that. Yeah. Any questions on that? We're gonna do an example.
For that example, does that mean that the contrapositive isn't equivalent for R is sufficient for S?
Oh, no, sorry. You could also write that as not S implies not, or not S implies not R. Totally fine. Good call. And the way you can look at that is if you don't have S, well, then you must not have R, because if you had R, you knew you'd have S. That's kind of the same contrapositive argument. But yeah, so this is necessary and sufficient conditions, just like that. Let's do examples. So for example, let's say R is equivalent to having a hammer. You have a hammer and you freaking know how to use it. R is having a hammer, and then S, your hammer certified, is you can build a house. Or, yeah. You can build a house, just like that. So, first of all, so let's see. Let's look at these two statements. Having, actually, let's talk about, actually, no, we'll do the statements first. So let's look at these two statements. R having a hammer is necessary to build a house versus having a hammer is sufficient to build a house. Which one of these is true?
Necessary.
Necessary, right? You need a hammer to build a house. If you have a hammer, doesn't mean you can build a house. I have a hammer. Okay, it took me 3 days to build a desk. Okay, so the point is, having a hammer is necessary to build a house, not necessarily sufficient to build a house. And so this part's not true. But what's the direction here? Does R imply S? If R, then S, or if S, then R? Based on these two statements.
S then R.
S then R. So this is an example of why we say R is necessary for S as opposed to S implies R. Right? Think about this example. Like having a hammer is necessary to build a house. So building a house is, or so if you can build a house, then you have a hammer. That's the direction it goes. Building a house implies you have a hammer. Make sense? Another example would be, let's say, having a working laptop and Wi-Fi is necessary to watch YouTube versus, and we're going to call this R and this S, versus having a working laptop is or having a working laptop and Wi-Fi is sufficient to watch YouTube? All right, which one of those are you thinking is true?
Sufficient.
The sufficient one, right? Having a working laptop and Wi-Fi is sufficient, but it doesn't mean it's sufficient, but you don't have to have it, right? I mean, you could have an iPhone and 4G or even 5G, right? Like you could have one of those things, or you could have a PlayStation connected to a landline, or whatever, right? So that is what's going on there. And with R and S, R being having a working laptop and Wi-Fi, and S being watching YouTube, does R imply S or S imply R?
R implies S.
R implies S. Absolutely perfect. So, what I was trying to point out with these two examples is that R necessary for S, that just means S implies R. R sufficient for S means not S implies not R. What time is it? Okay, we'll do one more thing and then we'll call it a day. We'll do 2.3 next time. Oh, can I erase that? I'm sorry. I'll erase the top first. Any questions on all that? Cool. So, last thing we'll do I'll say this. A, not equivalent. If A and B are two logical statements, for example, A could be a conditional statement, B could be its converse, something like that, right? If A and B are any statements that aren't equivalent, I'm sorry. Let's have A and B be logical operations. If A and B are logical, or these binary logical operations, it could be any operations that aren't equivalent, that does not mean that A of PQ is not equivalent to B of PQ for all possible P and Q. It means there is some PQ such that A PQ is not equivalent to B of PQ. Here's the point I'm trying to make. Saying that P implies Q is not equivalent to the inverse, not P implies not Q, that doesn't mean that sometimes sometimes a statement, doesn't mean sometimes a conditional statement and its inverse won't be true. They can be true. They can both be true sometimes. It simply means that it's not going to be true for all possible P's and Q's. Does that make sense? So being equivalent, that just means I can't say that this will always be the same at this. It might sometimes, it's not always going to be, right? Whereas saying that a statement is equivalent to its contrapositive, you know they're always going to be the same. So if you have P implies Q, you automatically know not Q implies not P. It doesn't matter what P and Q are. But if you know P implies Q is true, you don't necessarily know if the inverse or converse is true. It depends on what P and Q are. Does that make sense? It's kind of like if I say sine of x does not equal cosine of x, right? That means that like they're different functions. If you draw them, sine of x looks like this, and then cosine of x looks like something like that, shifted, right? Looks like that. They're not the same function, but sine of pi over 4 equals cosine of pi over 4, right? They intersect right here. So saying that these expressions are the same, that doesn't mean they're not ever going to be the same. It doesn't mean they're not ever going to line up. It just means they're not exactly equivalent. They're not the same everywhere. Like you can't say sine of x. You can't just say you have sine of x. You can't just say, oh, that is cosine of x, right? It depends on what the x is. Okay, I think it's making sense. Anyway, the very last example that this leads to is I told you that necessary and sufficient are kind of opposites of each other, but that doesn't mean they're not always. That doesn't mean that it can't both be true at once. It's like saying, let's have R is equivalent to being bald, or I am bald, and S is equivalent to, or let's say a guy named Dave again. Poor Dave. Dave is bald, and S is Dave has no hair. R is necessary for S. That's true, right? Like, being bald is necessary for not having hair. You can't have it any other way. But also, R is sufficient for S. That's also true. So this is the same thing as S implies R. This is the same thing as R implies S. So this is just like a statement and its converse being true at once. Or yeah, if a statement and its converse are true at once, what's that mean? That means thus R is a biconditional with S. R if and only if S. We call this R if and only if S, or we can say R is necessary and sufficient for S. However, it is past 5, so it's necessary for me to get off Zoom and stop talking about math. I will bottle it up and store it all and talk about it on, oh, Monday's Labor Day. I'll tell you the schedule. Tuesday. But anyway, yeah, any questions?
Just real quick, could you
Yeah.
actually do if and only if as like literally R if S and R only if S? Like,
Yeah, exactly.
okay.
Like, so R, this is the same thing as saying R if and only if S. This is equivalent to this and this. Because remember, these are two different statements. Saying two statements are not equivalent does not mean they're opposite. It doesn't mean that if this is true, this will be false, and if this is false, this will be true. No, no, no. It just means they're different, right? And so these are two different statements. If both of these different statements are satisfied at once, then we say it's a biconditional, R if and only if S, or we say R is necessary and sufficient for S. That make sense?
Yes.
Good question. Excellent question. I'm going to circle that actually. That's important. For example, if you're doing some logic in the future and you know this is true, you can say, oh, this is equivalent to this and this being true. Therefore, I know this is true, and then you can work with that. Anyway, that is the class. If there's no more questions, I'm going to stop recording. Okay, gonna stop recording.